it would not be much of an exaggeration to say that lecture 24B is the most important linear algebra content that we've had so far, because it's like a hinge connecting stuff that's come before with stuff that's going to come afterwards. Recent things, including eigenvalues, eigenvectors, similar matrices, basis, change of basis matrix, all those things are ultimately, because of this content, going to be used to help us understand both difference equations and differential equations. In fact, starting in this lecture, I'm going to include stuff about differential equations in lecture B's more often from this point on, more direct application of the linear algebra. Okay, so what is it about? You can see it's about something called diagonalizable matrices, diagonalization theorem or theorems, and then we'll apply it to two-dimensional example of a difference equation and a differential equation. This is really the key algorithm for quote-unquote everything. The reason I use quotes there is because it's not literally everything, but it's a lot. First of all, a definition. We say that A, an n by n square matrix, is diagonalizable if A is similar to a diagonal matrix D, which will also necessarily be n by n. I'm doing the definitions and theorems in the general case for an n by n matrix, but for this lecture at least, the examples are going to be 2 by 2. We will do some 3 by 3 and possibly 4 by 4 examples shortly to come. In other words, A is diagonalizable if there exists a diagonal matrix D and an invertible matrix P. This is the definition of similar, so that these two equations are true. The diagonal matrix is P inverse times A times P, which is equivalent to A equals P times D times P inverse. To get from here to here, multiply both sides of this equation on the left by P. P times P inverse is I, the identity matrix, which when you multiply it times A times P just gives you A times P. And also multiply both sides on the right by P inverse, and a similar kind of thing happens. You can solve for A. That is what it means for A to be similar to D. And if D is a diagonal matrix, then A is similar to a diagonal matrix, and we say A is diagonalizable. Why is this important? Well, recall that it is easy to raise a diagonal matrix to a power. General case here, n by n matrix. Here's your general diagonal matrix, that's n by n. All the numbers off the main diagonal from upper left to lower right are zeros. These are the only possibly non-zero numbers, though some of them could be zero, or in fact even all, if you were saying it's a matrix of all zeros, the zero matrix. In that case, d to the mth power, say, can be found by raising all the entries to the mth power. I guess you could say even including the zeros to the mth, because those would still be zero. Okay? When the matrix is not diagonal matrix, this is a much harder calculation to do. Diagonal matrices are special for both differential systems, equation systems, and systems of difference equations. It corresponds to completely decoupled systems, as we've seen before, and those are easy to deal with. Therefore, if A is diagonalizable, and if we can find the matrix P, then it is easy to raise A to a power as well. Why? That's not obvious at first glance. We need to use this equation and raise both sides to the mth power, say. And what happens is you get a bunch of cancellation. A to the m is P times D times P inverse to the m, which is this product where you've got m factors here in parentheses. And then by the associative property, you can do some regrouping. You can put parentheses around the P inverse times P. That's what I got there. And the next P inverse times P, you don't see another P, but there is one. That becomes this one, etc. There will be a P inverse times P in here as well. That becomes this one. And all those P inverse times P's are identity matrices. And as identity matrices, we can get rid of them with respect to multiplication and just write this. It's easy to figure out d to the m, excuse me. Therefore, to find a to the m by this, it's relatively easy too. I mean, these could still be painful calculations if p and p inverse are kind of big. I mean, finding p inverse could be difficult as well. But in theory, it's easy if you can find those things. Do p times d to the n times d to the m times p inverse. The diagonalization theorem, which is the only one that's called that specifically. There are other diagonalization theorems related to this that I'm going to talk about as well. Tells us exactly when A is diagonalizable. And it also gives us inspiration for an algorithm to do the diagonalization. In other words, to find P and D. Here's the theorem. An n by n matrix, excuse me while I take a drink of water here, is diagonalizable the assumption here is only with real number entries in matrices, so this is diagonalizable over the real numbers. If and only if, IFF means if and only if, it's equivalent to A having n linearly independent eigenvectors that are necessarily real eigenvectors as well. A is n by n. If it's got n linearly independent eigenvectors, not even bothering to say what the eigenvalues are, you just know that they're eigenvectors for some eigenvalues. If there are n linearly independent ones, then A is diagonalizable. And this is an if and only if. If there are not n independent vectors, such vectors, A will not be diagonalizable, and vice versa. If A is not diagonalizable, then A will not have n linearly independent eigenvectors. In other words, A is diagonalizable if and only if it has a list of eigenvectors that form a basis of Rn. Basis of Rn. Called an eigenvector basis of Rn. Furthermore, we can say that A equals P times D times P inverse, where D is a diagonal matrix, if and only if, again, the columns of P are n linearly independent eigenvectors. You put the eigenvectors into the columns of P. And if there's n of them that are linearly independent, we know by the invertible matrix theorem that that will be an invertible matrix. P inverse will exist even if it's a pain to find it. In fact, in that case, the entries on the main diagonal of D are the eigenvalues of A. That correspond respectively in the same order to the eigenvectors that are in the columns of capital P. Same order for the eigenvalues that you see the corresponding eigenvectors. We will look at an example here. Another theorem is based on this observation. We've seen before that eigenvectors corresponding to distinct eigenvalues are linearly independent. That was the theorem when we first started talking about eigenvalues and eigenvectors. You can also write the following theorem. If an n by n matrix has n distinct real eigenvalues, then it's going to be diagonalizable. This is not an if and only if. The implication goes this direction. If you've got n distinct eigenvalues, it's going to be diagonalizable. If it's diagonalizable, it does not mean that it has distinct eigenvalues. Simple example suffices there. Any diagonal matrix with, say, the same numbers on the main diagonal is already diagonal, therefore it's diagonalizable. You can take P to be the identity matrix. But it does not have, in this case, two distinct real eigenvalues. Maybe I should use something other than 2 here. It's got one distinct eigenvalue, 3, though it has a multiplicity of 2. So this is not an if and only if. It would mean, however, that if A is not diagonalizable, then there will not be n distinct real eigenvalues. You can say that. All right, here's an example of a matrix that we're going to diagonalize and then apply it to raising a matrix to a power. And then that can be applied to a difference equation. And then we'll also look at an application to differential equations. Okay? So the theory is important, but these examples are really important too. Diagonalize, these are directions for a problem here, if possible, this matrix. And also, if it is possible, find a to the 5th power. I was originally going to find maybe a to the 100th power, but the numbers are just way too big. Even a to the 10th power, they're kind of big. So I decided to go with a to the 5th. That wouldn't be too hard to do step by step, but let's do it in the more fun way, really, and that's using diagonalization. So let's write down the characteristic polynomial of this using the trace and determinant. The trace is 2 plus 1, which is 3. The determinant is 2 minus 12, which is negative 10. The characteristic polynomial is lambda squared, for a 2 by 2 case like this, minus the trace times lambda, minus 3 lambda, plus the determinant. The determinant is negative 10. And that can be factored as lambda plus 2 times lambda minus 5. The eigenvalues are going to be negative 2 and positive 5. So that's the first thing to do. Then you'd want to find the corresponding eigenvectors in the same way as always. Plug these eigenvalues, negative 2 and 5, into A minus lambda I. Consider the corresponding homogeneous system. Do row operations. If you plug in lambda equals negative 2, you've got to change, it's these two numbers from the original matrix that change. The other two stay the same. So the 3 and 4 on the off diagonal here stay the same. Lambda gets subtracted from 2 here and from 1 there. 2 minus negative 2 is 2 plus 2, which is 4. 1 minus negative 2 is 1 plus 2, which is 3. Row operations gives you this, which you can think of as x plus 3/4 y equals 0. So x is negative 3/4 y. That's a negative sign in there. X equals negative 3/4 times y. Y is free. If I pick y to be 4, this equation means x is negative 3. Again, eigenvectors are not unique. Any non-zero scalar multiple of this will also be an eigenvector for this eigenvalue and could be used to construct a different matrix P that also works. P is not unique, but it's sort of nicest to pick ones without fractions. For lambda 2 equals 5, again, the 3 and the 4 on the off diagonal from the original matrix stay as they are. Subtract 5 from the main diagonal. 2 minus 5 is negative 3, so it gives you the negative 3 there. 1 minus 5 is negative 4. Row operations, this is x minus y equals 0, therefore x equals y. Y is free. Pick y to be 1, you get this vector. So based on that diagonalization theorem, if we create a matrix P with, say, this is the first column and this is the second, I could do it the other way around too. That's another choice I have. That will be P that diagonalizes A to a matrix D, diagonal matrix whose diagonal entries are negative 2 and 5 in that order. Negative 2 and 5, and then zeros elsewhere. Well, so what are these matrices? I did create P by making V1 be the first column and V2 being the second column. Being a 2 by 2 matrix, I've got the shortcut formula for P inverse as the scalar 1 over the determinant of A, go back to A, 2 minus 12 is negative, not A, P. Determinant of P is negative 3 minus 4 is negative 7. Then you swap the numbers on the main diagonal, the negative 3 and 1 swap places, and you put negative signs in front of the numbers on the off diagonal. Simplify a bit, multiply negative 1/7 through, you get this matrix for P inverse. You may want to check that P times P inverse is the identity matrix. Therefore, D is P inverse times A times P. You can double check these calculations. Does give you this diagonal matrix. Take the time, pause the video, double check these calculations. I will just quickly check the product of these two. 2 times negative 3 is negative 6 plus 12 is positive 6. 2 times 1 plus 3 times 1 is 5. 4 times negative 3 is negative 12 plus 4 is negative 8. And finally, 4 times 1 plus 1 times 1 is 5. Check this one too. That is D. So therefore, what is a to the 5th? It would be, since A is the other way around, P times D times P inverse, a to the 5th is going to be P times D to the 5th times P inverse, as we saw earlier. There it is. Take the time to check these calculations too. There's your final answer. And maybe it's not less work than just multiplying A by itself with 5 factors, but it's more fun, I might say, and it definitely applies even for higher powers like 10th powers or even hundredths powers. It still works, but the numbers end up being really, really big. Okay? So that's raising a matrix to a power, but we've talked about how raising matrices to powers is important for difference equations. In particular, the general nth power will be important for solving a difference equation. There's nothing stopping us from finding a to the n for the example in the previous slide. Here it is. The general nth power, maybe I should have used m instead of n to stay consistent with the previous one, but we're going to talk about a difference equation here, so I will use an n. Nth power of a is a to the n is this, p times d to the n times p inverse. Because d is diagonal, I can just raise the numbers in the main diagonal to the nth power and make the other numbers still 0. Multiply it out, double check that you get this. And that allows us to solve this difference equation right here. Why? Because we've said the solution of the difference equation in terms of the initial condition vector, x0, is a to the n times x0. So since we have a formula now for a to the n, we have our solution of the difference equation, a to the n times the initial condition vector, which you can multiply out if you want. I did. You don't have to do that, but maybe you'd like to. This is a 2 by 2 matrix times a 2 by 1 column vector. This is a 2 by 1 column vector. This is not a 2 by 2 matrix over here. Just 2 entries. Notice the plus signs in there. One eigenvalue is positive, positive 5. One eigenvalue is negative, negative 2. With difference equations, things get weird with negative eigenvalues. You get some balancing back and forth. It's something that happens with difference equations that doesn't happen with differential equations. But in general, this vector would not approach the origin unless x0 and y0 happen to both be 0. So the origin is some sort of source that kind of bounces back and forth in some way. You could try graphing this if you want. Let's apply this now to a differential equation with the same matrix, so we get the same eigenvalues and the same eigenvectors. Consider the linear ordinary differential equation or system, this with the same matrix that we just looked at. We applied diagonalization to raising a to a power in the last 5-10 minutes. But raising a to a power is not helpful for differential equations. We would need the matrix exponential instead. By the beautiful generalization, that's the unique solution of this IVP, which consists of this differential equation plus this initial condition. The beautiful generalization, remember that's my name for the property that I'm talking about here. I think it's just so beautiful, so I call it the beautiful generalization. There's a discrete form, difference equation version of the beautiful generalization as well, that I actually even just used over there. So you may want to think about what that is. Notice this is the matrix exponential, e to the ta, where t is a variable. This is a function of time. It's a parametric curve. This matrix times that initial condition vector, where t is a variable, will generate a curve in the plane. Not talking about flows here at the moment. Thinking this is a solution curve. Can we use diagonalization here? Sure. Why? Well, for one thing, e to the t times d power is easy to compute. We've talked about this before too. Corresponds to completely decoupled systems. And we also saw Mathematica gave us this kind of output. You make it a new diagonal matrix whose entries of the main diagonal are e to the t times these numbers on the main diagonal, the eigenvalues of A, and zeros on the off diagonal. You get a diagonal matrix there. And also, since the Taylor series definition of the matrix exponential. Here are the details. Step by step, A is the same as this, where D is diagonalizable, or D is diagonal and P is invertible. Use the Taylor series expansion for the matrix exponential. You get the identity matrix of the appropriate dimension. This is a 2 by 2 system, so this would be a 2 by 2 identity matrix. In general, you could have an n by n system, and that would be an n by n identity matrix. Plus t times whatever that matrix is, plus t squared over 2 factorial times that matrix squared, plus t cubed over 3 factorial times that matrix cubed, etc. forever and ever. We're not worrying about convergence here. I think probably in 25B I'll maybe look at this convergence intuitively in terms of Mathematica's computations and see that partial sums of this seem to be settling down towards something specific. Maybe even for this example we'll do it. And, well, look at these things. These are like a to a power, a to the third power in this case. By the same property as with the difference equations, that's the same as p times d to the third times p inverse. So I'm using that in the next one. And I can be written as p times I times p inverse as well. And I'm keeping the constant inside the parentheses, the t here, the variable t squared over 2 factorial, I'm keeping it inside the parentheses. Because I'm trying to relate it to e to the td here, that's the reason. And assuming I can factor a p out of the left of this infinite series, and a p inverse out on the right of the infinite series, what I'm left with inside here is the matrix exponential e to the td, which equals this. So the matrix exponential e to the ta is p times e to the td times p inverse. Similar kind of thing as with the difference equations, except now we use the matrix exponential instead of a to a power. How does this work out? Here are the details. Here's e to the td. There's the matrix P, same matrix as before. There's the matrix P inverse. Same P as before, same matrix A, so it has the same eigenvalues and same eigenvectors. So I create the same matrix P, compute P inverse in this way. Keep going in the calculation. Multiply these two, for example. Excuse me. Actually, what I did was I multiplied these two to get this. Then I still have this matrix over here. Keep multiplying. I next multiply these two matrices to get this. Times your initial condition vector. And if you want to write that as one vector, you can do it this way, for example. Take the time to double check these things. I'm really struggling with dry throat now. I coughed last week and a couple weeks ago, but now it's a dry throat. It's October 20th here, and we're getting our earliest big snowfall that I can ever remember here in Minneapolis, St. Paul area. October 20th, 2020. 2020 seems like it's never going to end. First big snowfall really early. Even for Minnesota, this is really early. We usually don't get big snowfalls until November. All right. This is our last slide. We're almost done. Hang on. It has another theorem on it. The theorem's kind of long. It's got three main parts to it. Let A be an n by n matrix. Suppose that I've got distinct real eigenvalues and they are these numbers. P must of necessity here be less than or equal to n. If P equals n, then A has n distinct eigenvalues. These are the eigenvalues. And that would mean A is diagonalizable. But here I'm not assuming P equals n necessarily. It could be strictly less than n. I have fewer than n distinct real eigenvalues. Part A. The dimension of the eigenspace for lambda k, where k can be any one of these subscripts 1 through p, which you could call the geometric multiplicity of lambda k, the dimension of the eigenspace. Remember, eigenspaces are null spaces of A minus lambda I, and therefore they are subspaces of Rn. Typically, in most examples, the eigenvalues are distinct, and the eigenvectors are single eigenvectors. The eigenspaces are one-dimensional lines through the origin, typically, but not always. If some of these are repeated eigenvalues with algebraic multiplicity greater than 1, it's possible the geometric multiplicity, the dimension of the eigenspace, could be greater than 1 as well. But you can say in general that that dimension is less than or equal to the algebraic multiplicity of lambda k as a root of the characteristic polynomial. So that's saying if you got the characteristic polynomial and you factor it, and one of the factors is lambda minus lambda k to some power that I'll just call, say, I don't know, m sub k, the algebraic multiplicity of lambda k is m sub k. The dimension of the eigenspace for lambda k has to be less than or equal to that number. You might say typically it equals it, and typically this number is 1, but it could be less than. Next, part B, the matrix A is diagonalizable if and only if, this is an if and only if, the sum of the dimensions of these distinct eigenspaces equals n. P could be less than n, and each one of those could have a multiplicity bigger than 1, for example. But if the dimension of the eigenspaces happens to equal the algebraic multiplicity of the eigenvalue, the corresponding eigenvalue, then this will happen. The sum of the dimensions of the distinct eigenspaces will equal n, and A will be diagonalizable even though it's got repeated eigenvalues. And this happens if and only if, yes, like I just said, the dimension of the eigenspace for each lambda k, the geometric multiplicity, equals the algebraic multiplicity of lambda k. If the dimension for each k from 1 to p of the eigenspace equals the corresponding power here, mk. Last part, C. If A is diagonalizable, this is just a plain if implication rightward, not an if and only if. If A is diagonalizable and if bk is a basis for the eigenspace of lambda k for each k, so there'd be a b1 and a b2 and a b3 that are eigenspaces for lambda 1 and a lambda 2 and a lambda 3, etc. Then if you merge all those bases together, beta 1, beta 2, or b1, b2 through bp, take all the vectors in each of those bases and put them into one bigger set, it will form an eigenvector basis for Rn if A is diagonalizable. Excuse me. I'm wondering if this really could be an if and only if. It seems like maybe we could write a converse to this that might be true. For the moment, I'm not going to worry about it. Maybe I'll come back to it in lecture 25b. Okay, so diagonalizability, which I'm not even sure that's a word, is nice because it allows us to solve difference equations and differential equations more easily. But not all matrices are diagonalizable, real diagonalizable. In particular, if your matrix A has complex non-real eigenvalues, it will not be diagonalizable over the real numbers. If we allow P and D to have complex numbers, then it will be diagonalizable over the complex numbers in that case. But there are even matrices with real eigenvalues that are not diagonalizable. Try diagonalizing that matrix. It's got a repeated eigenvalue, 1, of multiplicity 2, algebraic multiplicity. Turns out the eigenspace for that eigenvalue has geometric multiplicity 1. The dimension of the eigenspace is 1. And that's going to mean it's not diagonalizable. Go ahead and try it. Try to find the corresponding eigenvectors. See if you can find 2 linearly independent eigenvectors for this matrix. For the eigenvalue lambda equals 1. You won't be able to do it. It's not possible. Okay? Doesn't mean you can't come up with a matrix P that's invertible and compute P inverse AP here. That could certainly be done, and A would be similar to whatever you get in that case. But you'll never get a diagonal matrix, which is pretty amazing when you think about it, I think, at first glance. Thanks for watching.